To talk about empirical mode decomposition, we need to firstly talk about the Hilbert-Huang transform. HST, a NASA-designated name, was proposed by Norton E. Huang. It is the result of the empirical mode decomposition and Hilbert spectral analysis. The HST uses the EMD method to decompose a signal into so-called intrinsic mode functions, IMF, with a trend, and applies the HSA method to the IMFs to obtain instantaneous frequency data. Since the signal is decomposed in time domain and the length of the IMFs is the same as the original signal, HST preserves the characteristics of the varying frequency. This is an important advantage of HST since real-world signal usually has multiple causes happening in different time intervals. The HST provides a new method of analyzing non-stationary and non-linear time series data. Coming back to empirical mode decomposition, EMD, it breaks down signals into various components. EMD can be compared with other analysis methods such as Fourier transform and a wavelet transform. Using the EMD method, any complicated dataset can be decomposed into a finite and often small number of components. These components form a complete and nearly orthogonal basis for the original signal. In addition, they can be described as intrinsic model functions, IMF, as mentioned earlier. Because the first IMF usually carries the most oscillating high-frequency components, it can be rejected to remove high-frequency components. For example, random noise. EMD-based smoothing algorithms have been widely used in seismic data processing, where high-quality seismic records are highly demanded. Without leaving the time domain, EMD is adaptive and highly efficient. Since the decomposition is based on the local characteristic timescale of the data, it can be applied to non-linear and non-stationary processes.